welcome everyone, and thank you very much for attending the latest in the series, the Spatial ML series of seminars. It's I have great pleasure to introduce you to Mario Doumet. Mario completed his master's degree very recently, Masters of Applied Science in ECE at the University of Toronto, where he was supervised by Vaughan Betts. And prior to that, he graduated with a Bachelor of Engineering in Computer and Communications Engineering from the American University of Beirut. His interests include computer architecture and machine learning algorithms. I first met Mario at one of the Spatial ML workshops, I think the first Spatial ML workshop, maybe, and he impressed me greatly. So it's great to have you here, Mario, and to hear that you've also finished your master's degree. So Mario is very much on the job market, I understand. So those of you from industry who are on the call, it's your chance to grab a superstar here. And Mario, we're very pleased to have you. So go ahead.
Thanks a lot, George. Thank you. So hey everyone, today I'm going to talk to you about H2PIPE, which is our take on a data flow architecture with an off-chip memory solution. So CNNs are a very popular AI workload. This is no secret. And they traditionally have different needs, whether it's for inference or for training. And for inference, traditionally, they require low latency, high throughput, and low precision. And these three characteristics make them an amenable target for accelerators. And on FPGAs, historically, there have been two main acceleration paradigms. There are PE-based architectures and data flow architectures. On a PE-based architectures, there's a set of relatively general PEs. And the PEs have to be general in order to process a wide range of functions and a wide range of kernel sizes, activation sizes. And so here the layers are scheduled onto the processing elements. So we have a first layer that is processed, and then after that comes a second layer and a third layer up until the network is completely processed. And so the processing elements have to be general to process all these different layer sizes, and traditionally this is implemented via some sort of instruction set architecture. On the other hand, data flow architectures have more specialized processing elements, where each processing element is targeting a specific layer in a network. And so in this case, PE1 is processing specifically layer 1 and wouldn't be able to process layer 2, but PE2 is processing layer 2 and PE3 is processing layer 3. So here, with all the processing elements processing in parallel, the granularity is usually smaller than a whole frame. It's usually something along the lines of one line or maybe even one pixel in some smaller cases. And you'd have all the processing elements at steady state processing in parallel, each with its own weight memories. So you'd have all the weight memories being read in parallel, and that can increase the bandwidth slightly. So overall, data flow architectures do have specialized PEs, and that in turn yields better compute utilization, and that makes it a good fit for FPGAs. However, because all the processing elements require their weight memories, and each weight memory is read approximately once per cycle, that creates very high bandwidth requirements, and traditionally this has been satisfied via the use of on-chip memory. So if we take a look at the previous data flow CNN accelerators, or the biggest ones, we find that all those that use on-chip memory support smaller networks. So the MobileNet V1, the smaller YOLOs. And there have been attempts to support larger networks via the use of weight reloading, but that in turn compromises performance. And so our goal today is to take a state-of-the-art data flow accelerator that previously supported only small networks and try to get around that on-chip bottleneck. And so the advantages would be twofold. First, we would be able to get that high throughput data flow performance on the larger networks, and the larger networks are typically more accurate. But another advantage of this is that if we scale down to smaller FPGAs that previously could not even handle a small network like MobileNet V1, we'd now be able to support MobileNet V1 via the use of an off-chip memory solution. So the goal is to get that high throughput data flow performance by bypassing the on-chip memory bottleneck. So I'm briefly going to talk about H2PIPE before I dive into our solution. H2PIPE generates automatic network-specific hardware. It takes in a CNN TensorFlow graph and a configuration file, and it composes an accelerator that is a data flow accelerator with specialized PEs. In doing so, it gets good compute efficiency, and it deeply pipelines the network to get a high Fmax. It uses a wide range of hardware-aware optimizations. For instance, it leverages AI tensor blocks on AI-optimized FPGAs. So in our case here, we're using an Intel FPGA, and the granularity of inputs is 80 bits. I'm going to come back to this value later because it comes in handy. So please hold on to that 80-bit value. Another thing H2PIPE leverages is interconnect registers. So on Intel FPGAs, there is interconnect registers embedded in the routing, in the switch blocks, and at the input of connection blocks. And these make it so signals can cross the chip without going into an ALM, and that makes for better timing. There are other hardware optimizations that are listed here and also not listed here, but overall, all of these make for best-in-class performance. So what we propose today is H2PIPE, which is H2PIPE with an augmentation for HBM, and it's the first work to augment the CNN data flow architecture with high bandwidth memory on FPGAs. The goal is to take a state-of-the-art CNN accelerator that only processed small networks and make it process large networks. We first start by analyzing HBM. HBM is a 3D stacked memory. In its most basic form, it has 4 DRAM dies with 16 pseudo-channels total, each having a bandwidth of 16 gigabytes per second. Because there are so many pseudo-channels and so many wires, it's impossible for the wires all to be connected in one small point. And basically, the wires span a long part of the top of the chip in the image that you see on the right-hand side. In the chip that we target, there are 2 HBM stacks, so one at the top and one at the bottom. And the one at the bottom also spans a big chunk of the bottom part of the FPGA die. And this, in turn, imposes physical considerations that we take into account, and I'm going to come back to that later in the talk. So there are 2 main consumers of on-chip memory in a data flow accelerator. There are wait buffers and activation buffers. And to reduce the on-chip memory consumption, we can offload either to HBM. Offloading the activation buffer is going to require writing to HBM and then reading back, and that in turn will cause increased latency. While it seems that waits would have to pay the same price or a price similar to that, waits only have to be read, so they don't have to be written. But more importantly, their access pattern is entirely deterministic and known in advance. For that reason, we can cover the latency with buffering, and by prefetching the waits, we can have the waits ready in a buffer that's deep enough, and we would have to pay no latency overhead. If we take a look at the largest networks that we intend to support, for instance, or some large networks that we intend to support, some of them simply require too much memory and will never fit on on-chip memory, even on the largest FPGAs. So in this case, we have VGG with 1,200 megabits. And so the weights will have to be offloaded. Now, the question that remains is, should we offload activations as well? And if we take a look at the percentage of activation memory versus wait memory, we find that activations don't represent a significant enough chunk of the memory consumption. And for that reason, we choose to offload weights exclusively. One more thing is that we characterize bandwidth and latency in the paper, but here I'm just going to go over the bandwidth. Our first conclusion is that simulation models lines up with hardware models. So it's like the light blue and the dark blue are fairly close to each other, and then the light green and the dark green are fairly close to each other, although the simulation model is a bit more optimistic. The access pattern that we use here is a random access pattern. And the reason for that is we assume that we're going to have multiple layers accessing a single pseudo channel. And so their access pattern and their address streams are going to be interleaved and changing constantly. And so at worst, it's going to be a pseudo-random access pattern or a random access pattern. And for that reason, we do take a worst case analysis here. But what we do find is that we should use a burst length of greater or equal to 8 to get that good bandwidth efficiency, where the read efficiency is above 80%. And we're going to go back to choosing a specific burst length in the results section after running some experiments. Okay, so I've talked about HBM, and we've chosen to offload the weights. But now what we need to do is to be able to deliver the weights from point A, which is a pseudo channel, to point B, which is a layer. And for that, we need to create a weight distribution network with two goals. The first goal is to have high bandwidth and utilize the HBM bandwidth efficiently. And the second is to have high frequency so as not to hurt the design frequency. Regarding the bandwidth, each pseudo channel can provide 256 bits per cycle. And each layer engine or tensor chain uses 80 bits. And I mentioned that previously, it's the granularity of a tensor block. So each pseudo channel can easily support 3-layer engines. That would be 240 bits per cycle. And so we for each pseudo channel, in the worst case, we can feed 3-layer engines. And I draw them out here in blue, green, and yellow. I also mentioned that we need a burst length greater or equal to 8 for good efficiency. And so what you see here, those FIFOs are burst matching FIFOs. Their depth is proportional to the burst length that we choose. So if we choose a higher burst length, we're going to have higher resource utilization because those FIFOs will be deeper. We also need to cover the latency of the reads. And so we need to have FIFOs that are deep enough. We use 512 deep, we call them last stage FIFOs to cover the latency. And to get better timing, we duplicate those FIFOs and add a lot of pipeline registers. And so these FIFOs that you see that I just drew are duplicates of each other to avoid very high fanouts, and there's a lot of pipeline registers in between them. One problem with this design is that if we use it as it is, the tensor chains will sometimes do erroneous computation because the HBM is non-deterministic. And because it's non-deterministic, it's possible that the whole layer engine runs out of weights because of some HBM stall. And we need to be able to freeze the computation because previously on-chip memory was deterministic, and now this entire system is no longer deterministic. And so the simpler way would be to use a clock enable. But on the Intel FPGAs, the interconnect registers don't have clock enables. And so imposing a clock enable on the design will preclude the use of these interconnect registers and create horrible timing on the design. So what we do instead is that we use the clock enable on the AI tensor blocks only and incorporate a stop mechanism into the control logic where we don't have to actually use the clock enable port. One last thing from the architecture perspective is we still need to write the weights to HBM, but we only do so once. And so we'd like to minimize the resource utilization of such an operation. So we reuse the image input buffer and serialize the write path and do some optimizations to minimize the resources consumed. Okay, so we now know how to deliver the weights from point A to point B, but we haven't quite specified which layer is point B. So namely, there's a lot of layers, and we can offload all the layers to HBM. But what we propose here is a hybrid system where we offload some of the layers to HBM and some of the layers to on-chip memory. That's because they're good for different things. So HBM has higher capacity but lower bandwidth than on-chip memory, and on-chip memory has lower capacity but higher bandwidth. So in that sense, HBM is fit for layers with large kernels and low bandwidth requirements, traditionally the layers in the latter part of the network, fully connected layers at the end of VGG16, for instance. On the other hand, on-chip memory is fit for smaller kernels with higher bandwidth requirements, traditionally layers at the beginning of a network. But to better quantify that and to avoid these hand-wavy approximations, we create a score metric that gauges which layers are best fit for HBM. And so using that score metric, we offload the layers with the highest score to HBM until we run out of HBM bandwidth to allocate. And that way we guarantee that the layers that do end up on HBM, with their weight stored on HBM, are the ones most fit for HBM. All right, so we've chosen which layers go to HBM, but we haven't chosen to which pseudo channel they're connected. What I mean by that is that if we take a look at conf2d16, which is that green layer in the middle of the FPGA, conf2d16 can be placed anywhere on the chip, but can also be connected to any pseudo channel. And if we connect it to pseudo channel 0, it's going to have a very different effect than if we connect it to pseudo channel 31. And the place and route engine is going to have a more difficult time in one of these scenarios. So what we want to do is to create an assignment that minimizes the amount of distance that the weights have to traverse. And in that sense, we would be able to avoid having very long buses that span a big part of the chip. What we propose is a clockwise arrangement where we assign the later layers to the bottom HPM stack and going from right to left, and then the top HPM stack is used by the earlier layers. And the reasons for that are there's two main reasons. The first is that, as I mentioned previously, the layers offloaded to HPM are traditionally later in the network. And the last layers of a network are almost always on HPM. And these layers have to be close to the PCIe interface, but also close to an HPM stack. That means that those layers are best off being on the bottom HPM stack. The other reason is that the earlier layers of a network are usually stored in on-chip memory. And that means they have no spatial restrictions and can be placed anywhere on the chip. And they can help us scale the chip vertically to reach the top HBM stack so that when a layer in the network does need to use it, the pipeline is already much closer to the top HBM stack. So for those two reasons, we propose a clockwise assignment. So let's take a look at the results. And first off, the effects of our clockwise arrangement. So in the bottom left, you see that PCIe interface. Now I'm going to draw out what the clockwise arrangement became after place and route. It looks somewhat clockwise. At the end, specifically, it looks very straightforward with the line going from right to left. But what's more important here is if I draw out the distance traveled by the weights, we want to make sure that that distance is minimized. So if I draw out these black arrows, you see that the black arrows are fairly short. And in that sense, that means that locality has been maintained. And the layers are indeed close to the HBM channels, and that in turn makes for better timing and higher Fmax. So in that sense, the clockwise arrangement was a good idea. I also promised to come back to the burst length. So if we take a look at the burst length and its effect on ResNet 18, we find that it has no effect on the throughput. And the reason for that is the bottlenecking layer of ResNet 18 resides on chip. And so changing the burst length is not going to affect the throughput of that bottlenecking layer. And so we keep the burst length at 8. For ResNet 50, the bottlenecking layer has its weight stored on HBM. And so there, changing the burst length is going to affect the throughput. And what we find is that by increasing the burst length from 8 to 32, we get a 3% logic utilization increase, but also a throughput increase of 2%. And so it's a trade-off, but in this case, we choose a burst length of 32. So let's take a look at the throughput numbers. Here we compare throughputs where, in the first case, all the weights are stored on HBM, so we don't have a hybrid design. And then we compare that to a hybrid design where we use on-chip memory. And we find that using on-chip memory can get us speedups of up to 2.3x. And in the case of ResNet 18, and even 27% in the case of VGG16. So leveraging on-chip memory was an important optimization. We also want to gauge how good the results are. So we come up with an upper bound. It's hard to upper bound the hybrid design because there are so many parameters, there's so much on-chip memory, but we can more easily upper bound the all HBM versions. And the upper bound is a very theoretical one, but it's the available bandwidth divided by the memory traffic of the network, because we have to load in the weights for every image that's processed. And this upper bound is very unrealistic because it assumes unlimited compute. It assumes that there is perfect memory efficiency. It assumes that every single pseudo channel has a useful weight loaded every cycle and computed immediately. But nonetheless, when we compare ourselves to that upper bound, we find that we are within 23% in the case of VGG16, and at worst, within 32% in the case of ResNet 50, which means that H2PIPE leverages the HBM bandwidth very efficiently to be that close to a very theoretical upper bound. And the memory efficiency on its memory efficiency on its own is going to be like 90%. So it's impossible to be within 10% almost of the of that upper bound. So to be within 23% is a good achievement. Lastly, we also want to get an idea of how well H2PIPE scales as we add more HBM stacks. So in this case, we had 2 HBM stacks, but what if we had 4 available today on our chip? So would H2PIPE scale, or would the improvements taper off? So what we do is we run simulations until 85% logic or DSP utilization is reached. And we find that for the larger networks, we can get up to a 2x improvement in throughput. Well, for ResNet 18, because the network almost has all its bandwidth requirements fulfilled using on-chip memory, because it's a smaller network, the gains are more modest. We only get a 10% increase. Nonetheless, this shows that H2PIPE scales as more HBM bandwidth becomes available. Let's now compare our throughput results to prior work. So if we compare our ResNet 18 throughput results, we find that we outperform the best prior work by 19.4x in throughput and upwards of 4.5x in latency. On ResNet 50, we outperformed the best prior work by 5.1x in throughput, although two works do outperform us in latency. And the reason for that is ResNet 50 is a very deep network, and because we deeply pipeline for every layer, that causes an increase in latency when the networks are very deep. And for BGG 16, we outperformed the best prior work by 10.5x in throughput and close to 2x in latency. Overall, I've shown that data flow architectures can scale to large networks with high throughput. We've chosen to offload the weights, and we've described an efficient distribution networks to deliver the weights from a pseudo channel A to a layer B. We've chosen those layers so as to maximize the HBM bandwidth via the use of a selective layer offload algorithm. And we chose locality-aware assignments to minimize the travel of the weights across the chip. Overall, combining all these improvements yields a throughput improvement of around an order of magnitude over best prior. Thank you very much. And you can find the code is open source on GitHub, and please feel free to ask any questions.